So my name is Don Berndt, like toast, and I'm a professor here in the Information Systems Department, and I do data mining research and data warehousing research mostly. I'm also co-founder and chief scientist of SiteWit, the people who sponsored this room. Today, I just have a goofy talk that actually is a sort of lesson from several research projects that I've been doing. And in particular, I titled it, and this came this week, so this is fresh, first time I'm doing the talk, and I'm gonna try to improve it, but I've been noticing a pattern in a lot of the work I've been doing that is actually an intersection between man-made artifacts and data mining, and that I've been able to been able to build better systems these days by using man and machine in a tightly integrated loop for building things. And so that's what today's talk is about. It's sort of just some observations and some reports on some projects. Basically, the agenda is this. I have some new slides that are basically a brief history of natural intelligence, a brief history of artificial intelligence. Has anyone, do you guys know what the AI winter, the term AI winter means? Anyone at all? So we'll go into that, and then basically kind of a look at naturally inspired AI. And that's usually called biologically inspired AI, but there's an interesting new conference that occurred a couple years back, and they have now an acronym for naturally inspired AI. And so I want to talk to you a little bit about that. But more importantly, then I want to look at sort of tightly integrated hybrid systems and sort of some interesting observations from a couple projects. And this is the sort of group of projects. The first is information foraging theory, which James McCart is a colleague, friend, and former PhD student. And his dissertation was on information foraging theory and the sort of use of sort of animal foraging behaviors applied to people's navigation of websites and following scent trails through the web and things like that. And it was sort of biologically inspired and things like that. Then right after that, I was working on an algorithm at SiteWit for website chunking. And basically, we found that structure and the trails that people sort of walk through websites was just as good, if not better, than some of the mining approaches that we were doing. So we combined them and got a really interesting algorithm that chunks websites into pieces in a really smart way. And that actually let us do some data mining at a better level and really improved a lot of things for us. So then, we actually went, our research was also in text mining, and we were doing some work in text mining, and we came up with an idea of using sort of giant graphs of terms in text mining. And that actually ended up working pretty well, but we wanted to take a next step, and it came about through using authorship of documents to improve things. And so got another lesson there. Then we were working on some optimization problems for SiteWit, and started looking at naturally inspired optimization techniques, things like genetic algorithms, and found a really big win there. And so, after 4 times, I learned a pattern, and getting smacked in that many times. And I started thinking, well, it's sort of an interesting lesson that man-made artifacts, sort of thoughtfully constructed artifacts in machine learning loops really boost performance a lot. And so I then chose 2 examples, the online marketing optimization and sort of hybrid text mining to go in. But I was going to choose all 4 and make source slides, but I just didn't get them done. So I'll work on those as well. And AI is like a boomerang in my life, I should say. And basically, I started out as a C++ programmer. And then I became a Lisp programmer right around the time the AI winter started and managed to time my learning to become a master Lisp programmer with the market crash in Lisp. And so I'll show you some of that timing. But I started out as a biologist, then I went to become a computer scientist, and I kind of have run away from AI a few times when I got disgusted with the results of that. But like a boomerang, it comes back. So this time I'm just accepting the fact that it's going to be in my life as I go through computer science biology. And so that's what the storyline is. So it's a little flaky, and so I apologize for any flakiness in the middle. So our story starts when we walked out of the muck and sort of learned to breathe, and we began to exhibit natural intelligence. From cognitive science side, basically what happens is our brain got kind of more and more interesting until we finally reached an apex brain point that allowed us to do some really clever things. So natural intelligence is exhibited by anything with a brain. And we'll see some very simple brained creatures exhibit really interesting behaviors that we use in our website. So then man walked upright, okay, and developed the Lisp machine, one of the really incredible achievements. There was a Lisp machine company called Symbolics, and they built basically a high-speed hardware implementation for Lisp. And the sort of top point at programming was then to be able to program Lisp and AI and sort of hardware machines like this. They were super expensive and very, very fast for that. Of course, the whole market crashed in the AI winter. And so basically what it is Gartner Group has something called the hype cycle that you may have seen before. And basically, this is, almost all technologies follow this AI, follow this in a more volatile way if it's possible. So basically, you sort of get to a peak of inflated expectations. You drive down to the trough of disillusionment, and you come back up to the slope of enlightenment, and then you eventually find productivity. And this is sort of a fairly famous, well-known hype cycle. And AI followed this tremendously. I timed my Lisp programming back for the peak of inflated expectations in 1987, late. I was probably a master Lisp programmer. That year, the Lisp machine market crashed and the AI market crashed, right? And that was it. That was my first sort of really interesting, sort of super research-oriented job. And so I wrote that down. But of course, AI produced a lot of really interesting things. So all sorts of things that you probably use in programming came out of AI, right? All the search algorithms, machine learning technologies, data mining, speech recognition, language processing, all sorts of stuff. Statistical text mining that we'll talk about, and then artificial life and everything. Lots of stuff came out of it. It's just the AI winter was basically when funding dried up and the technical companies all went out of business and things like that. So there was sort of a horrible, sort of freeze in the industry, though many things survived out of that. And so that sort of gives us the sort of the background of this. And so when you go and to do something like that. So then what I wanted to move on to was thinking about, okay, that gave rise to artificial life and some of the search algorithms and things that were actually biologically inspired. So now there's a sort of an emerging name, naturally inspired artificial intelligence, and there's some conferences around this space. And basically, what we try to do is draw inspiration from the natural world while creating these artifacts, right? And so I was interested in using some genetic algorithms early on, and I've dabbled in this area for a while. But for the first time, I've used these to solve some really interesting business problems. So, so this is actually the idea of a bird flock. And this is sort of a visualization of flocking birds and things like that. So artificial life and a lot of the AI technologies try to use sort of influences like this to think about it. And think about how this explores a search space, right? This is actually a bird flock swarming behaviors and things that are very, very efficient ways to search spaces. And so we were looking at some problems, and you're trying to think of how to do this. So we looked at this as a source of inspiration for doing search algorithms. I'm just going to leave that open, just thinking that this is going to be a problem on 2 other slides. So, together. And by the way, just please make this a conversation. So if you feel like interrupting, please do. Okay. So that's it. So the idea here is that there's really one important lesson. Right? It's more of an observation. That's what I was thinking of afterward. Is that drawing more than just inspiration. We can take these systems and tightly couple sort of artifacts of natural intelligence with artificial intelligence, and lots of human behaviors produce interesting data. And I was starting to think about the fact that there's like first order input and second order input and really third order input and things like that. Things that directly influence the systems and then some that don't. And I'm just trying to think if I can actually get access to a video. Let me think about how to do that while I'm talking. And so that's it. So first example comes from SiteWit itself, the company. And if those of you who just attended the talk in there, kind of discussed a little bit about the company, but basically we optimize, we monitor and optimize online advertising spends and use mathematical optimizations to improve the bidding process and things like that, to improve campaign performance. So we actually have to think about how to optimize portfolios of things like keywords and ads and other things like that. And so in the advertising space online, there are things like the search engine result page and the placement of ads and things like that. And really, when you think about a huge amount of human effort goes into that. The ad copy itself is a creative process, right? Choosing keywords, deciding on bids and things like that in an auction, very, very, sort of important decision-making process. The refinement of keywords, again, a lot of creativity involved in that. So human thought is in a lot of places. Same thing with things like display advertising, retargeting. You have to come up with the creatives and other things like that. So there's a huge amount of a sort of natural intelligence being used to both create content and actually run auctions and things like that. So the idea is, okay, that's something that we can capitalize inside there. And then we look for a way to optimize that approach, to bring mathematical optimization into the process. And then we can look at things like bird flocks, genetic algorithms, and other things like that to bring into that process. So basically, like sort of the first book I looked at for optimization was David Goldberg's book on genetic algorithms for optimization. And so I remember writing, as a student, a couple of genetic algorithms to do some optimization. They've been used for a long time and very successfully in a lot of optimization processes, especially things that are changing and dynamic and things like that. And there's nothing more dynamic than human involvement in negotiations and auctions and other things like that. So this is actually a place that we could use evolutionary algorithms. So here we have a naturally inspired AI technique, and we have man-made artifacts that we can use, and we put them together to do this. And so our solutions at SiteWit are actually based on things like this, evolutionary algorithms. And so we have it. This is supposed to run. This is actually a visualization James created. It's our first visualization. It's actually a little, I'll take responsibility for being a little rough, better than he certainly delivered more than what I was going to deliver. But we're working with the Visualization Center to try to get that. But I'm not sure this is going to run, and I'm going to have to go find this video. And so in the interest of making the presentation a little less, it's an MP4 movie, and I don't know why it's not playing. But that's it. But basically, this is a giant search space. Let me just describe the process of what's happening. It's a giant search space of solutions to a portfolio of advertising that you're thinking about doing with a budget constraint on how much money you want to spend. And the goal is to try to find a balance in that portfolio that achieves really, really good results. And so we're going to couple sort of genetic algorithms, flocks of birds, sort of naturally inspired techniques with man-made data that comes out of, huge amounts of data that come out of that, and we're going to couple those together. And so this will actually flock and find a solution up in this corner that is actually the best solution like that. And I bet you it doesn't flock, but if the other one didn't run, I imagine this one's not going to run too. So we'll try to figure out what happens. What's that? I do, but then I have to exit this and then retrieve it. And so I thought maybe what we do is I'll go through a little bit of it, and then I'll go back and I'll find the video and I'll run it for you. It seems like a smoother way to approach that problem. I have another flocking video in a little while. And so we'll do that. So that's what's happening. That'll actually flock and find that after hundreds of generations, I've forgotten how many generations this one ran, but it's a couple, I think at least 100. And that's it. So that's the approach we use in SiteWit, okay? This sort of second example that I chose to focus on is text mining. So I took that slide to take a look at, and basically this research is at the VA. So this is not the SiteWit research, but this research is at the VA. And we do text mining on medical record notes. There's a huge effort going on to try to uncover information in the medical records that come from textual elements. It's a very complicated process. It takes a lot of work to do the text mining itself, but the results have been very, very good. And the VA is a kind of a leading group in that area. They have something called the Consortium for Healthcare Informatics Research, and they fund a lot of work in this area. And it's a sort of nationwide center, multi-site nationwide center, including Stanford and the VA out there, and Vanderbilt, the VA there, Yale and the VA, Boston, I think Harvard Northeastern, and a couple other groups like that. Portland, Indianapolis, and the Regan Street Institute, and the group out there, and just a lot of collaborators. So it's really interesting. And so I chose this slide just to start with, because just to get you the lay of the land, because I'm not sure how much text mining you've been exposed to and things like that. So usually people in text mining discuss text mining as sort of a more top-down approach, things like natural language processing versus statistical approaches that are bag of words approaches and statistical models. The first disillusionment I had was I was doing natural language programming with parts-of-speech, really very for story understanding. And we actually had a lab where we'd study young children who would come in and read, and you're supposed to learn from how they were acting and then go write computer programs that looked and sort of acted like them. And it was just horrible work. It was like failure after failure and tedious beyond belief. And so I actually just fled the area, and I went to statistical approaches and kind of went back to school to get my PhD in data mining and things like that. And now I find, again, like a boomerang, sort of back here. And so James and I actually do more statistical approaches, but we actually now do natural language processing as well. And actually, the sentence boundaries and things like that, all ideas that span them, is very, very difficult to get around that. In fact, actually, we're right now doing a paper on the quality, sort of looking at injecting errors into the text and mining them and things like that, and trying to find the quality curves. And we've been really surprised at how robust the statistical techniques are and things like that. So that's under the VA, and this is it. And so this is the second example that I decided to try to use to illustrate this. And basically, so natural language understanding is an area that I worked in and fled. Statistical sort of approaches, and then first data mining, then statistical text mining is where I ended up. And but we started thinking about hybrid systems. Like, so is there a way to use NLP-like toolkits and statistical approaches to put them together? And so we started thinking a lot about that, and we came up with a new algorithm, which eventually I think we'll put into open source inside maybe RabbitMiner, but we're putting some open source things out. And so what we did was we got started actually mining medical records. And our first project was actually to find falls, people at risk for falls. Fall injuries are among the worst things that can happen to people, especially veterans. The trajectory on your life and your health care and your quality of life is horrible once you have really injured yourself on a big fall like that. And so it's a really important area to look at. And so what we did was we went ahead and we actually started doing text mining, statistical-based approaches. And it's a simple problem because there's some dominant terms like fall and fracture and other things like that. But we got actually really good results early on in this, and we actually even have better results now, thanks to James. And so we actually started out doing things like that. And what happens is these approaches surface terms like this. And so this is actually a network, and just I stuck a couple of network pictures in here to seed your mind with the idea that these are terms, concepts that exist in fairly large networks. And so that's it. So terms that would have to do with fall are some vectors of terms and some terms, things like falling, or FX, the abbreviation for fracture, or the term fall, things that you would actually fall over, like sandbags, rug, electrical cords, devices, throw rugs misspelled, things like that, actually, and things. And so those are things that surface just automatically from text mining, which is really amazing. And so we've been really pleased with the results, and we're able to do a lot of work on extracting information from medical records. Now the NLP stuff is more like a human, right? It's top down. So the idea is you would parse a bunch of text, use the sentence boundaries, recognize parts of speech and things like that. And then you're going to do a term lookup or concept lookups, like to define concepts. And you would use a big resource like the UMLS, the Unified Medical Language System, right? And you actually it's actually driven by the knowledge base that you have. In medicine, we're lucky to have things like the UMLS, which is the result of decades of effort by very talented and expensive MDs and psychologists and things like that. And that resource is clearly a man-made artifact, right? You can't get a more carefully man-made artifact, right? It's the result of a large amount of focused natural intelligence at the human level, right? Not the bird level like our flocks, but at the human level, and that's what's going on. So that UMLS can be looked at like as a large graph. And so if you think about it, this pretty picture is the snow cone picture, and it is actually a piece of the UMLS. And so when you think about that, you think about other giant networks like the internet and things like that. And so there's a lot of power in the creation, and this is one of the really interesting man-made artifacts that you can have. So what we did was started thinking about, well, can we capture sort of crowdsourced insights like this? Can we capture the amount of information and use it in the statistical process? So we started thinking, like, how can we inject something from this giant network into the statistical process? And so we started first, our first efforts were actually to think about using things like PageRank, hits, and some of the algorithms that you see from Google and other internet search engines and things like that. And we thought, well, couldn't we do some computing like that and find an importance measures for each of the terms? And so the idea is, instead of just looking up a term, right, we actually use the graph to provide importance. So instead of just looking up a website, right, or a page, you try to find something that rates importance. So what we tried to do was the same thing with terms in the giant graph created by UMLS, okay, or embodied in UMLS. And so that's sort of what we did at first. So we tried to think about how to do that, and we can kind of see that we'll see in a second, we had sort of some rough starts there and some flaws in that first logic that are. So basically the idea here is that you look up terms in these giant graphs like fall or fracture, pain or risk and things like that, and they have PageRank values, right? They have weights, and so they're going to vary in importance. And we're going to use this information and inject it into that. So we're going to take graph-like information, inject it into the statistical text mining process. And so we were hoping this would work. So the statistical text mining process is basically, and these slides are thanks to James, is basically a set of documents. So if you can pipe in on any of these slides. So we take a set of documents and create a term by document matrix. And so basically in here, what we're going to have is counts of all of the terms and their occurrence in the corpus, in the related documents. So nothing but frequency counts, okay? So bag of words based approach to statistical text mining uses nothing but counts like that, okay? So there's no like higher order, no natural intelligence in that. It's just counts, right? And that's it. So the idea is to sort of think about taking that term and injecting statistical weights into that. And so what we do is we take that term, we look up the weights from the giant graph, and we combine those into a sort of weighted graph, or weighted matrix, right? The weighted graphs like that. And what we're going to do is then use these rather than that. So essentially what you have is no longer just a simple count, but you have a count adjusted by the crowdsourced intelligence of the people who built the vocabulary themselves. So the hundreds of people who contributed, or thousands of people who contributed to building that vocabulary and carefully constructing the edges on that graph and by hand putting relations in there have created a resource that we can compute over, produce the results of, and this is what I would call a second order natural input, right? Is that it's computed over that graph, results in a weight that actually summarizes all of the many authors of that vocabulary, and then we feed it into the statistical process. So the statistical process uses the same resource as an NLP approach, but instead of using it just to look up individual terms, it uses it at a giant network to compute the weights. And so that's how we injected things like that. You want to add anything to that? Or?
No, I think you do.
Well, I belabored it completely, so I should have covered at least some of it by now. And that's it. But basically, our first results were really quite good, and our next results are going to be much, much better. I'm confident in that. And so basically, we had a baseline, and basically by putting that extra natural intelligence into the process, we actually boosted our text mining results very well. So we basically took graph-based weights, combined them with statistical weights, fed it into a machine learning method, and then predicted things like whether you will fall, whether you're at risk of fall or not, or whether you were a smoker or not, and things like that, right? We actually, kind of did that with text mining. So, any questions at all at that point? So the problem was that this graph isn't really great, okay? The problem is that those people that create the graph, all those physicians and everything, were trying to build this graph, this vocabulary for natural language processing, for term lookup. They weren't thinking about this as a generic sort of resource. They weren't thinking about it as hybrid natural and artificial intelligence, right? They were actually thinking of it as sort of NLP-based approaches. And so the idea here is that what can we do to add more to that graph if we're thinking more in the mindset of hybrid systems, using natural intelligence and artificial intelligence? So at a USF basketball game, having heard the stinging criticism from James's presentation at one of our national meetings, we sort of said, how can we rescue this and do a better job, right? The idea is that graph is weak. Really, to be more technical, it had only sort of limited hierarchical relationships. It wasn't really that interesting a graph, right? So we came up with this approach, which is actually being pursued right now. We're running our first results. So basically, it has a second order effect or an input that we're taking advantage of from natural intelligence. What we did was we retrieved all of the abstracts from PubMed. So basically, PubMed is a huge resource of online, I think that's going to be a little late on that one. But anyway, what we're doing here is PubMed is actually a huge resource of the repository of all the online medical articles, all the scholarly articles or things written about medicine, get recorded in PubMed or made available through PubMed. And what we did was we pulled a huge amount of the abstracts, so a very targeted set of text. And we chose abstracts for a reason, okay? If you write a scholarly article, you spend a lot of time, after you write the article typically, thinking about how I would express that article in a paragraph or two, right? 400 words, 200 words, whatever the abstract limit is, right? And that is, so these are really well-chosen words by really smart scholarly authors. And so you're thinking, okay, this is the apex of natural intelligence, right? These are the self-selected, really smart people that irritate you in class. And they write articles, and they put a lot of effort into this one piece, okay? We take this and we look for all the term co-occurrences that occur in this paragraph, right? And we generate links and pump all of those things in there, millions and millions of links into this graph. So now the graph, instead of the 500,000 or so, or million, no, 1.1. How many links? Right?
We had 400,000.
500,000. Yeah. So we'll round 400 to 500,000. It's not. It's plus or minus 100,000 among friends, right? And that's it. So instead, we're having, I think, 5 million links from.
Maybe 8 or 9 million or something.
But I thought we were going to limit it down to 5, right? Yeah. Okay. So an order of magnitude more links. So I'll have to get my story straight on that. So an order of magnitude more links get generated from this really nice author effort, and it pumped into this graph. So now this graph, instead of being 500,000 edges and things like that, is 5 million or 10 million edges. Huge amount of new information made available like that. So right now, we're actually using this graph, and then I want to use it to do some tasks. some text mining tasks, and some information retrieval tasks. And so the idea is that can be used for things like medical record navigation. If you want to help a physician or provider go through the medical record, find the most important things and stuff like that, information retrieval like that is really important. If we could use this resource to make that a much more intelligent process or a much more accurate process, it's a really big win. So what we're using is that. Now, the second thing is we're going to then revisit our regular text mining work, try to find people at risk for falls or who suffer from post-traumatic stress disorder, another big focus area for the VA, and we'll try to use this new algorithm for that. So it's really a new algorithm. We call it MO for macro ontological engine because actually, because you always want to pick a very complicated thing, but it's actually an ontology giant graph. And instead of doing a micro lookup, it's a macro perspective on that and computes things like that, like search engine-like measures. So macro ontological engine is what I came up with. He shares no fault for coming up with stupid acronyms like that. When you think about it, the medical records is made up a lot of structured information. So if you come into the hospital, there's a diagnosis is made. There are codes, right? You know, like the ICD codes or International Classification of Disease or CPT codes for terminology codes, and those get put into a medical record, but they're of limited they express a limited amount of information, right? And now they are adding a lot more codes, and it gets very specific in some ways, but there's not a lot of nuance in that, and so the medical record structure always lags, and a huge amount of information in medicine is in notes, like clinical notes. So there's a kind of rules about, within 24 or 48 hours, you want to have a note attached to the medical record and things like that. So a huge amount of clinical data, and especially the nuanced data, is in the medical record. So, for instance, you were asking more like a surveillance task would be to find all of the people who are maybe at risk for falls and try to send them to a fall clinic before they have a really injurious fall, right? Or when you might think about PTSD, the symptom sets for things like post-traumatic stress disorder overlap with other mental illness. Sometimes it's hard to find the differences and things like that. Maybe you can try to find people who have been overlooked as far as post-traumatic stress disorder and things like that, and surface those. It could be used for things like medical record navigation. We were just talking about more information retrieval and things like that. And so navigation within a patient set of records for a lot of different tasks like that.
What do you mean by navigation?
Well, so you open a medical record, right? And some of the records have 5,000 notes in them. Okay, you're there trying to treat that patient. Some are really old, some are really new. You typically use things like time proximity like that. You look up, but having some kind of, like a search engine. What's the thing? Make sure I don't miss the really important things. And think about things like post-traumatic stress disorder, which are traumatic injury, brain injuries like TBI, maybe you played football and you got hit twice and you had a concussion. It could be some of that stuff could be really old and could have been mentioned on the first visit 3 or 4 years ago, for a veteran or something like that. So all that stuff is really important to think about as far as that goes. I guess my opinion, this is speculation and nothing, no science here, right? It's just that there's been a lot of efforts to influence the way people do medical records, and especially the writing process. Not a lot of them have been really successful, and some are downright destructive in some sense. And so we have a project right now, so one of the things to make it easier for people to write medical records is you actually allow them to generate templates and put like canned pieces. And so when you think about it, okay, we have a problem. We have the stuff that you guys know from your database class, the structured data, right? And then you have free-form, sort of natural language expressions in the notes. But if we've kind of missed something, we have that in between where maybe we could generate a table or a set of 5 questions that are kind of structured information, but we shove it into the text. And we have all of these artifacts in the text now that are sources of confusion that our NLP systems really have hard time processing because they're fragments and things like that. So we have a project that also identifies those pieces and tries to handle them differently. But I do think that in general, this whole suite of techniques, and hopefully our algorithm, would be used outside of this to try to do exactly what you're saying, to try to improve those algorithms. And so on our list, to-do list is actually to try some things not in medicine with this eventually. So there's a lot of evaluation techniques. So some of you may have taken data mining and things like that. There's actually a lot of statistical measures you use, a lot of techniques like tenfold cross-validation or cross-validation approaches where you subset differently to try to get, to try to hedge against just plain bad or good luck in the selection of things like that. And so we use a lot of techniques like that. And then we usually run a fairly rigorous thing. So we'll label data. So one of the sources in here, I abbreviated the slides. I wasn't sure how long things would go. So there's a big annotation process where we have clinicians read medical records and label them and things like that, which is another natural intelligence group, input, right? And that's like a first order input. And we segregate that data, leave some unseen, test on unseen data and things like that. So there's a lot of techniques for that. And in fact, actually, the project we're just doing right now has two physicians for the information retrieval. And so when you say just a second about how that's going to be evaluated, because we have basically a test that they're going to run, right? And that's it. So even the annotation, like to capture the natural intelligence part from these really expensive resources, like medical doctors, is actually part of the process of trying to do good evaluations like that. And so we spent considerable sum hand annotate record and medical record notes, from clinicians like that. So we have, good data to use. And so that I kind of omitted that part from the presentations because I was just trying to be fast about it. So that's it. So in summary, this second example was basically a look at hybrid text. And you can kind of see again, okay, a little less on the biological, inspiration, but heavily man-made artifacts, the results of a huge amount of derivative information, like scholarly article information, codified, quantified, and injected back into a machine learning process. Again, I think a really interesting example of man-machine learning systems, right? That again, the point is that they wouldn't do as well on their own. So this is sort of the end. I would like to just mention the two other examples that I didn't put into the slide set because I did in just a second. The first is that website chunking one. Basically, a part of the data mining process, we have an automated data mining process in SiteWidth. And if you look at all sorts of web analytic data, it's always at the page level. And the problem is that the page level on some websites is a very, sort of way down in the weeds, right? There's thousands of pages, product websites and things like that. And so we found that if you kind of go to a higher level of abstraction and kind of categorize the pages, you can get a better data mining result. And so the problem is, how do you do that? And so, we originally thought, okay, well, we'll build first we were going to do the mechanical Turk route, or, we were just going to basically farm out, classify the pages and that's it. Or people and so we had actually to budget for a huge amount of labor in that process. And so we thought about it, and we were then thinking about maybe building a machine learning solution that actually just took a data set of pages and sort of labeled that. But it didn't work very well. And so in reflection, though, you start thinking, okay, by then I had been beaten over the head with the information foraging theory thing, the stuff at the VA, and I'm thinking, wait, what's my rule? My rule is to look for naturally intelligent artifacts to couple closely. I'm not talking a little coupling, I mean close coupling, right? And so we started thinking, so what do we have? Well, every time someone goes through a website, they navigate it, there's usage data, right? You have actually the trails that people left, right? And then when people build websites, they're usually smart people, right? They structure the websites in ways that, like you guys are engineering, right? You engineer the website in a way. And so we have structural and sort of usage information. And so we coupled that together and used that to chunk and create web, sort of page categories, website chunks. and then feed that into the data mining process. So again, naturally intelligent, human behavior produces artifacts that you can use. And then we apply machine learning on top of that, right? And that together gives you much, much better results. And so we were able to solve a problem that we had budgeted in our startup funds a huge amount of capital to dedicate to labor, which we just never spent. And so it was an awesome win as far as that goes. So we had a really, really great time. So at SiteWit, James McCard's at actually SiteWit and the VA, and he was also here at USF. And actually, I should have put biology as well. I should have put USF, SiteWit, and the VA, but I was around 2 in the morning finishing the slides. So I think I may have read. At the VA, we have Don Finch, Jay Jarman, Steve Luther, a group of researchers there, and that's it. We have a new online program. My chairman asked me to mention this. We have a new online program, and I'm going to click on that link in a second. But I'd like to leave you with a really inspirational video from the space of things. And this one, I'm just going to click on this because I'm thinking it's not going to run on my computer. And so this is actually I was blown away by this video when I saw it. So. These are the starlings, they're murmurations, of starling murmurations. It's the weirdest one though. It's just amazing how amazing the search space is that you go through.
What are they looking for?
They're just trying to look at, so a lot of people study this to go ahead and write a computer program that simulates this. So the first video I showed you was actually a computer simulation, which is almost impossible to tell the difference. It's almost impossible to tell the difference. So, so a lot of people try to think about this. Okay, you would think, okay, the starling is, I'm going to be politically incorrect here. The starling is several notches below us on natural intelligence time. I'm going to go out on a limb. And so the idea is that how do they produce such coordinated behavior? And those simple rules can produce beautiful artificial life and behaviors and things like that. And then we can learn something from this. And basically the idea is that these are efficient ways to search large spaces and things like that lend themselves for stuff. So we could solve optimization problems like this. And so actually that's what we do. Our optimization algorithm is a lot like a naturally intelligent system like that. So that's sort of what that was meant to show. Mm-hmm. It's actually worked really, really well. It's again, we're not okay, remember, that's a naturally produced input to a machine learning process. And the machine learning process is pretty robust as well. And so we're able to kind of not worry too much about that. Okay, so what's important is to get out of the weeds and sort of see the trees, right? And that, if we accomplish that, everything else becomes stronger. Well, that's the end of my talk. I don't know if you have any other questions, anything at all. So that's the experience that I've been having in man-machine learning and things like that. So hopefully that shows you a couple examples of how that's fit together in my life. And I think it's going to be an interesting year coming up. So looking forward to investigating some more of these problems. Well, thanks a lot for coming.